Right now, we are 75 meters beneath the world's busiest shipping lanes between France and England. 5 million tons of freezing saltwater are pressing down directly over your head. A single crack, no thicker than a human hair, and the sea would pulverize this space in a heartbeat. Down here, there should be nothing but crushing darkness. And yet, we are standing inside a miracle of concrete. How was it possible? Imagine digging a tunnel 75 meters beneath freezing, violent waters, stretching 38 kilometers, with $15 billion on the line. Above you, millions of tons of seawater press down, shipping lanes churn, and between you and a catastrophic watery grave lies just inches of reinforced concrete. For 2 centuries, this was considered impossible, a suicide mission that broke banks, claimed lives, and defied nature itself. Then, in 1990, 2 men, one British, one French, reached through a tiny hole in the rock and shook hands. They had conquered the impossible. But the real story isn't the handshake. It's the high-stakes gamble, the robotic monsters that labored in darkness, and a secret layer of prehistoric chalk that held the fate of 2 nations. This is the Channel Tunnel, a project so massive and so dangerous that it remains the benchmark for what humans can achieve when we stop fighting the ocean and start moving beneath it. But before the first shovel hit the ground, the project was already destined for failure. The English Channel is a 22-mile stretch of unforgiving ocean. For 10,000 years, it has been a wall. Napoleon wanted to cross it with horse-drawn carriages lit by oil lamps. Hitler developed plans to launch a surprise invasion through it. Every attempt failed because the sea always wins. Until 1986. That is when the UK and France finally agreed to fuse their economies and their geography. This wasn't just a tunnel. It was a 50-kilometer subterranean marathon consisting of 3 separate tubes, 2 main rail tunnels and 1 central service tunnel. But to build it, they needed a miracle. They needed to stay dry while surrounded by billions of gallons of water. The key was geology. Engineers discovered a specific layer of earth called the chalk marl. It was the Goldilocks zone, stable enough to hold its shape, yet soft enough to chew through. And most importantly, it was largely watertight. If they stayed in the marl, they lived. If they drifted just a few meters too high, they hit porous rock, and porous rock means the ocean comes inside. To hit this target, they manufactured 11 tunnel boring machines, or TBMs. These weren't just machines, they were city-sized monsters, each over 800 feet long and weighing 1,500 tons. The cutter head alone featured hundreds of cutting edges made from tungsten carbide, one of the hardest materials known to man. On the British side, at Shakespeare Cliff, they had to move 250,000 cubic meters of rock just to create a launch base. On the French side, they built a vast 60-meter-deep circular pit. But as soon as the machines began to turn, reality set in. The French side was a nightmare. The seabed there was riddled with faults and fissures. Seawater under immense pressure, equivalent to 12 atmospheres, began to leak into the machines. Imagine being miles from the shore, hearing the groaning of the earth, and watching saltwater spray through the seals of your machine. The waterproofing failed. The electronics stalled. The project was 9 months behind schedule and billions over budget before it even truly began. This is where it gets serious. The British side anticipated drier conditions, but even they weren't safe. Fissures appeared that hadn't been detected in the surveys. To survive, they used a technique called grouting. They drilled probe holes 250 meters ahead of the machine. If they hit water, they injected a chemical grout into the rock to seal the cracks before the massive cutter head ever arrived. It was slow, painstaking, and terrifying work. Inside these unventilated tunnels, the temperature could hit 50 degrees Celsius. It was a pressure cooker miles from the sun. But how do you maintain precision when you are drilling blindly toward a common point from 2 different countries? GPS doesn't work through 75 meters of solid rock. 1 fraction of a degree in error would mean the tunnels would miss each other completely, ending the project in a global embarrassment. Reports emerged that during one critical phase, the ends were off by 12 centimeters. Panic spread. To solve this, engineers turned to space-age laser guidance. A laser theodolite hit photosensitive targets on the TBM. If the machine drifted even a few millimeters, the computer would scream an alert. They also used a far more ancient method, fossils. Paleontologists were stationed on site to examine the excavated muck. By identifying specific microscopic fossils, they could confirm exactly which layer of the chalk marl they were in, ensuring they didn't drift into the deadly porous rock above. As the months turned into years, the tension between the British and French teams grew. They weren't just fighting the Earth, they were fighting the clock and mounting debt. The project was privately funded, and every delay put the entire venture at risk of bankruptcy. By 1990, the two teams were only a few hundred meters apart. This was the moment of truth. They stopped the massive TBMs and drilled a narrow pilot hole. When the drill bit from the UK side broke through and met the French side, the relief was astronomical. The alignment error was less than 50 centimeters. Over 39 kilometers of subterranean drilling, they had achieved impossible precision. But then came the problem of the machines themselves. These TBMs were designed to move forward, not backward. They were too massive to turn around and too expensive to dismantle. The solution was a final, dramatic sacrifice. The British machine was steered downward, away from the tunnel path, and driven deep into the bedrock. It committed mechanical suicide, buried forever beneath the English Channel to make way for the French machine to complete the final breakthrough. It remains there today, a silent $15 million ghost. The construction phase was over, but the hidden systems were just beginning. A tunnel of this length creates a unique physical problem, the piston effect. As a high-speed train enters, it pushes a massive wall of air ahead of it. To manage this, engineers installed 194 piston relief ducts to equalize pressure. Then there was the heat. Trains generate immense friction. Without intervention, the tunnels would reach 60 degrees Celsius. Engineers had to install the world's largest air conditioning unit, 2 pipes carrying chilled water that continuously absorbed the heat. But the greatest fear was always fire. In 1996, the nightmare became reality. A fire broke out on a shuttle and temperatures spiked to 1,500 degrees Celsius, hot enough to melt steel trucks into lumps of metal. The concrete lining began to fail. But the 3-tunnel design, criticized by some for being too expensive, saved everyone. The central service tunnel was maintained at a higher air pressure, preventing smoke and flames from entering and creating a pressurized sanctuary for escape. The final price tag for this miracle was $21 billion in modern currency. It was a financial disaster for the original investors, who saw costs spiral as every unforeseen obstacle added millions. Yet, it was an unparalleled success for the continent. It removed the wall of the English Channel, turning a treacherous sea crossing into a 35-minute routine. Today, over 20 million passengers a year travel through this prehistoric layer of chalk. They sit in comfortable seats, likely unaware of the buried robotic monsters beneath them or the 12 atmospheres of pressure held back by the concrete just inches away. The engineering of the Channel Tunnel changed our understanding of what is possible. It showed that with enough tungsten carbide, laser precision, and sheer human will, even the most violent natural barriers can be conquered. We often think of the world as being divided by geography and borders, but this tunnel proved that those barriers are only temporary if you are willing to dig deep enough. And yet, the ocean remains unpredictable, always patient, always testing. Even now, monitoring is permanent and maintenance is constant. Subtle shifts in the seabed create pressures that the tunnel must breathe through. What was once a blueprint became a living system. We have the technology to bridge the world, but do we have the political and economic will to stay connected when the ground beneath us starts to shift? Because the sea may not have won this time, but the Earth is always waiting to take back what we've borrowed. And that changes everything.